pleasant day to everyone. Today we will tackle a discussion about the weathering and its components. Although it may sound complex to your ears, but here's the rockers to make it easy for you all. Let's go for another J Adventure quest. For learning objectives in this today's lesson, first is identify the process and causes of mechanical and chemical weathering. Next is identify the different types of rocks. And lastly, list the various examples of rocks.
What is weathering? Any familiarization? Weathering is the process that decomposes rocks and converts them to loose gravel, sand, clay, and soil. It involves little or no movement of the decomposed rocks and minerals. However, loose and weathered materials offers little resistance to rain or wind and easily erodes. To give an insight into weathering is responsible for many rocks, arcs, and hoodoos or lumpy columns, such as those found in Utah Arcs and Bryce Canyon National Parks.
There are two types of weathering, the mechanical and chemical weathering. Started with mechanical weathering, which is also called the physical weathering. It reduces solid rocks to small fragments but does not alter the chemical composition of rocks and minerals. Think of this. The fragments of rocks that has been crushed using a hammer are no different from the parent rock, except they are smaller. It's called the mechanical weathering, which means breaking rocks into smaller bits without changing what they're made of. Some factors trigger the occurrence of mechanical weathering, such as a pressure release fracturing, frost wedging, abrasion, thermal.
Pressure release fracturing. Pressure release fracturing occurs when rocks form deep underground fracture as they near the Earth's surface due to reduction in pressure. For example, when a granitic pluton solidifies from magma deep beneath the surface, it undergoes intense pressure from the overlying rock. As tectonic activity uplifts the granite over time, the pressure decreases. Erosion then removes surface layer, further reducing the pressure on the granite. This decrease in pressure causes the granite to expand and develop cracks or joints. This phenomenon, typical in igneous and metamorphic rocks, significantly influences geological processes such as weathering and erosion.
On to the next cause is frost wedging. It is the mechanical disintegration, splitting, or breakup of rock by the pressure of water, freezing in cracks, crevices, pores, joints, or bedding planes. In colder regions, when water freezes in rocks and crevices, it expands, leading to fracturing and formation of frost-ridden rocks. The surrounding rock is compressed by this expansion, causing it to split and fracture. This process, known as frost wedging, commonly occurs when water can seep into rock crevices, freeze, and expand, gradually breaking the rocks apart. Frost wedging is responsible for the creation of mountains and boulders with wide fracture in cold temperature areas.
Abrasion is a process of wearing down or scraping away material through friction. It occurs when two surfaces come into contact and rub against each other, causing the removal of small particles from the surface. Abrasion can also occur in natural environments such as the erosion of rocks by wind or water. The Grand Canyon provides the best example of abrasion in rock. The Colorado River flowing through the canyon carries a significant amount of sediment and rock fragments. As the river flows, the fast-moving water carries these rock fragments downstream, causing them to collide with the canyon walls and bedrock. This constant impact of these rock fragments against the canyon walls has led to the abrasion and erosion of the rocks, gradually wearing them down and shaping the cliffs and rock formations that characterize the Grand Canyon.
Rocks at Earth's surface are exposed to daily and yearly cycles of heating and cooling. When temperature changes rapidly, the surface of a rock heats or cools faster than its interior, and as a result, The surface expands or contracts faster than the interior. The forces generated by this thermal expansion and contraction may fracture the rock. Thermal expansion is the increase in length, area, and volume of materials when they are subjected to increase in temperature, while thermal contraction decreases in length, size, volume of a substance as it gets cooled. Here is the illustration. After identifying the causes of mechanical weathering, let's dig into another type of weathering, which is chemical weathering, which will be discussed shortly.
Chemical weathering is a process by which air and water chemically interact with rock, altering its composition and mineral content over time. This is akin to the rusting of a steel knife blade where the final product differs both physically and chemically from the original material. Key processes involved in chemical weathering include dissolution, hydrolysis, and oxidation, water, along with acid bases, and oxygen in the atmosphere or water sources facilitate these processes gradually decomposing rocks over geologic timescale. For instance, how slightly acidic rainwater dissolve minerals in rock, like granites or marble, eventually causing them to break down or crumble over time. This process changed the rock appearance and composition.
Next is hydrolysis. It is a type of chemical reaction that occurs when water breaks down the chemical bonds of minerals in rocks, leading to their decomposition. The bonds of H positive and OH negative ions in water reacts with the minerals, resulting in the production of a weak acid. This process weakens the rock and makes it more susceptible to disintegration. Example of hydrolysis includes the breakdown of feldspar into clay minerals when water comes in contact with granite. The feldspar crystals react with water and are chemically altered, forming clay minerals that weaken the rock.
Oxidation is a chemical process where substance loses electrons, leading to an increase in its oxidation state. Understanding how oxidation works involves grasping the fundamental principle of electron transfer and changes in oxidation states like electron loss, oxidizing agents, oxidation state change, redox reaction, electron flow, and energy release. One of the examples of oxidation is in rock is the weathering of iron-rich rocks. This process that occurs when iron-bearing minerals such as iron oxide or sulfides present in rocks undergo oxidation when exposed to oxygen and water over time. This causes iron to minerals to react with oxygen in the presence of water to form iron oxide or hydroxides that will result in iron minerals leading to the formation of rust-colored stain on rocks, indicating the presence of iron oxide. This process altered the composition and appearance of the rocks over time.
Chemical and mechanical acting together.
In desert, salt cracking is known to occur due to the presence of dissolved salts in surface water and groundwater. Granite undergoes a process called exfoliation, where layers of weathered material split away like layers of an onion. Exfoliation is often attributed to pressure release fracturing, but some geologists propose that hydrolysis expansion may be the main cause. During hydrolysis, minerals like feldspars and silicates react with water to form clay. The addition of water causes clays to have a greater volume than the original minerals. Also, on the other hand, erosion occurs when weathered rocks are transported to a new location by rain, wind, running water, glaciers, or gravity. These agents of erosion can carry the material over long distances and deposit it as a sediment layers. Weathering breaks down bedrock and organic materials from plant that contributes to the creation of soil at the earth's surface. However, soil does not accumulate and thicken over geologic time. If it did, Even if it did, the earth will be covered in a thick layer of soil and rocks and will not be present on the surface. Instead, interaction with water, wind, and glacier erode soil as it forms. Additionally, gravity can cause weathered material to slide downhill. As a result, erosion removes soil at a similar rate to its formation. As a result, then, the soil is usually only a few meters thick or less in most parts of the world.
Another factor of rock movement is mass wasting, which refers to the downhill movement of the earth material, primarily triggered by gravity. The term landslide is used to describe both mass wasting and the landforms that are formed as a result of it. While gravity exerts a constant force on all slopes, the strength of rocks and soil typically keeps the slope stable. However, mass wasting naturally occurs in hilly or mountain areas, with steep slopes being particularly susceptible to landslide. Then, why do landslides occur?
Causes of slopeness.
Several factors result in the slope of a rock. Water is one of the reasons that affects ironing, because water is a substance that can seep into the soil or rock and replace the air in the pore space or fractures. Since water is heavier than air, this increases the weight of a soil. Vegetation influences slope stability by removing water through transpiration. To illustrate, imagine a rock and dirt-covered hillside. Water penetrates the soil after a hard rain, filling in the spaces between the particles and adding weight to the soil. This added weight may increase the slope susceptibility to instability, particularly if the soil is saturated. On the other hand, the vegetation in the area, such as the grass and trees, actively draws water via their roots and releases it into the atmosphere through their leaves. The impact of plants and water on slope stability is described in this. Water displaces air, and when it penetrates rock or soil, increasing the weight of the soil. Slopes may become more unstable as a result, particularly in saturated soil.
Earthquake and volcano earthquakes and volcanoes can both have significant impacts on slope processes and contribute to slope instability. Earthquakes, which result from the release of energy in the Earth's crust, can cause ground shaking that leads to slope failure. The shaking can destabilize, lose, or weakly consolidate materials on slopes, causing them to slide or collapse. Additionally, earthquakes can trigger liquefaction in water-saturated soils, where the soil behaves like a liquid and loses its strength, further contributing to slope instability. Volcanic activity also plays a role in slope processes. Volcanic landslides can also occur as a result of unstable volcanic materials or the destabilization of slopes due to volcanic activity. The specific impacts of earthquakes and volcanic activity on slopes depends on various factors such as the type of materials involved, slope steepness, and the intensity of the seismic or volcanic events. These natural processes highlights the importance of understanding and monitoring slope stability in areas prone to seismic and volcanic activity to mitigate potential hazards.
Now let's proceed to the gravitational force. A gravitational force is the force that pulls all objects towards the ground. Gravity is a force of attraction between any two objects. Slope failure in mass waves happens when the gravitational force exerted on a slope exceeds the resisting force. The strength and cohesion of the slope material, the degree of internal grain friction, and any external slope support are among the resisting forces that contribute to the slope stability. The combined effect of these elements determines the shear strength of a slope. Gravity acts with the shear strength of a slope. Instability results from the gravity's vertical action combined with a component that acts parallel to the slope. The probability of the mass waves increase with the slope angle. The angle of repose for unconsolidated material typically falls between 25 and 40 degrees. The solid rock that is unweathered typically makes the slope steeper than 40 degrees.
Sedimentation is the process of settling or deposition of solid particles carried by a liquid or gas. When the velocity of the fluid carries the particles, decrease the particles settle due to gravity, leading to the formation of sediment layers. This process is crucial in geology, environmental science, and engineering. An example of sedimentation can be observed in bodies of water, such as rivers, lakes, or oceans. When the water flow slows down, suspended particles like sand, silt, and clay settle at the bottom, forming layers of sediment. Over time, these layers can build up and create sedimentary rocks through process like compaction and cementation.
A basin is a geological feature characterized by a depression or dip in the Earth's surface, resembling a bow with the highest sides than the bottom. They can vary in shape from oval to circular, akin to sinks or tubes and may contain water or remain dry. Basins are formed by both surface and subsurface forces, including erosion, seismic activities, and their creation can span from thousands of years to almost instantaneous events.
River drainage basins. These areas drained by a river and all its tributaries. A river basin comprises numerous smaller watersheds which are essentially miniature version of the larger basin. Each stream and tributary within the river basin has watershed draining into larger bodies of water like river, ponds, wetlands, and lakes. Example, the Mississippi River Basin in North America, which include various tributaries like the Missouri and Ohio rivers as well as smaller watersheds within them. Structural basins. These form due to the deformation of the Earth's crust, resulting in downward, de-sloping structures. They often occur along fault lines or as a result of tectonic activity. Example, the Williston Basin in North Dakota, USA, form as a structural basin due to the subsidence of the Earth's crust.
These are vast depressions on the ocean floor, covering the majority of the Earth's surface. They are formed through the processes such as seafloor spreading and plate tectonics. Sample, the Atlantic Ocean Basin, which is the second largest ocean basin on Earth, formed as a result of separation of North America and Eurasian plates.
The Mississippi River has transported vast amounts of mud and sand to the northern part of Gulf Mexico, resulting in the accumulation of sediment. Over time, the sediment has compacted and cemented, forming sedimentary rock. As more sediment is deposited, the weight increases, burying the lower and older layers. This burial process raises the temperature and pressure, causing changes in minerals and texture, transforming the sedimentary rock into metamorphic rock. As the basin sinks further, new layers of sediment bury the metamorphic rock to greater depths, where the increasing temperature and pressure continue to alter the rock, transforming it further. And if the temperature rises significantly in the future, the metamorphic rock may melt and form magma. The magma can then rise and solidify, becoming an igneous rock.
We hope that we make the complex topic easy for you all if you're struggling. We provided some glossary to better understand unfamiliar concepts. Once again, we're the Rockers in your adventure quest.